All right, this problem's new, so let's give this one a go. So a spare is launched at 35 meters per second. So I am going to show this. Sphere is being launched at 35 meters per second. And it's landing here, which is 100 meters away. All right, so here is what we're looking at. So for part A, all right, it is going to ask us, at what angle was it launched? So we are going to try and figure out this angle. All right, in order to do that, we are going to use the range equation, which might be new, which you can see here. So let me explain how this works. R stands for range, which is how far it is. This is initial velocity, this is sine of 2 theta, and this is g, which is our acceleration due to gravity, which is always 9.8 meters per second. So I'm going to come down here, and let's start solving it. So I'm going to rewrite the equation. Range, like I just said, equals initial velocity squared times the sine of 2 theta over our acceleration due to gravity. So let's start plugging some numbers in. So what's the range? How far did the sphere land? It was 100 meters away, so we replace r with 100. Our initial velocity is what it's being thrown at, which would be 35 meters per second. We got to square it. All right, times sine 2 theta, part of the equation, over our acceleration due to gravity, which is 9.8. All right, so we want to get this right here, theta by itself. In order to do that, we got to get rid of this divide by 9.8. The opposite of that is multiply by 9.8. Whatever we do on the right, we must also do on the left. So 9.8 times 100 gives us 980, okay? Equals 35 squared is 1,225 times sine of 2 theta. All right, next thing we want to do is get rid of 1,225. So whatever we do on the right, we must do on the left. Sine of 2 theta equals 980 divided by 1,225, which should give us 0.8. Now, to get rid of this sign, all right, technically we're kind of dividing by it, which just means we do the inverse, okay? So we're going to do sine, the inverse of sine, which looks like this, times 0.8. In order to do that on your calculators, if you go to Desmos, right, double check always by hitting the settings and making sure it's in degrees. All right, you go to functions, you're going to hit sine with the -1 over there, and we are going to do 0.8, which is going to give us 53.13. All right, so 53.13 equals 2 theta. Get theta by itself, we divide both sides by 2. And this will give us our angle, which our angle is then equal to 26.57 degrees. So we now know the angle. So we can go up here and we can put 26.57 degrees here. And now it's pretty similar to other problems that we have solved. All right, so let's separate into vertical as well as horizontal axis. All right, so the vertical axis, we're going to try and figure that out first. So that would be this side right here. So based off our angle, it's opposite over hypotenuse. So that would be sine SOHCAHTOA. So sine is the sine of 26.57 is equal to our opposite, which is x, what we're trying to solve for, over our hypotenuse, which is 35. Multiply both sides by 35, and this will give us 15.66. All right, so I can replace the x right here. That x is equal to 15.66 meters per second. Now we're going to do the same with the horizontal. All right, so we're trying to figure out this side. So based off the angle, that is going to be adjacent and hypotenuse. So that would be the ka in SOHCAHTOA. which would be cosine. So we're going to do the cosine of 26.57, all right, equals our adjacent, which is x, over the hypotenuse, which is 35. To get x by itself, we multiply both sides by 35. And this will give us 31.3. All right, so we know that the x over here is equal to 31.3 meters per second. Okay, so now we're going to move on to B. What is the maximum height reached? So that is going to pertain to the vertical component of the problem. All right, so we know our initial velocity when it comes to the vertical motion is 15.66 meters per second. The acceleration due to gravity is always going to be 9.8 meters per second squared, or meters per second per second. We are trying to figure out the height, so I'm going to put a question mark next to change of distance, and our final velocity is going to be 0, because when it gets to its max height up here, it is going to stop for that fraction of a second. So we know the final velocity will be 0. All right, so we have to find the equation that does not have t in it, which would be vf squared equals vi squared plus 2a delta y. We start plugging in our numbers, which would be 0 squared equals our vi, which is 15.66 squared, plus 2 times 9.8, and then we're trying to solve for our distance and the y component, so we leave it like that. All right, 0 squared is obviously 0. 15.66 squared should give us 245.24, plus 2 times 9.8 gives us 19.6. Change in distance drops, okay? So to get rid of a plus 245.24, we minus it. 0.24, whatever we do on the right, we do on the left. All right, so then we get negative 245.24 equals 19.6 delta y. Divide both sides by 19.6, divided by 19.6, and our distance should equal 12.51. I know you'll get a negative, but that's okay to just use positive for this. All right, so that would be part B. Maximum height is 12.51 meters. Now C, what is the total flight time? So we are simply looking for T. All right, so in order to solve that, we know that our initial velocity on the horizontal component is 31.3 meters per second. We know our distance, how far the spear landed, which is given here, is 100. And now we are just trying to figure out how long it was in the air for. So I'm going to put t equals question mark. So we just use velocity equals distance divided by time. So 31.3 equals 100 divided by t. We're going to cross multiply. 1 times 100 is 100. 31.3 times t is 31.3 t. Divide both sides by 31.3, and we should get our answer of 3.19 seconds. And that would be C, 3.19 seconds. All right, I hope this helped.